me and my wife in our house, in our yard, we're dealing with, I don't know, moles, voles, gophers, something. They're digging up our yard. I wonder how many moles there. I hope it's not moles. They're really ugly. I wonder how many moles there are. Voles are cuter than moles. I hope it's voles. Okay, maybe voles are smaller. Let's pretend it's voles. I wonder how many voles there are in our yard. To tell you the truth, I have no idea. But if I wanted to be patient enough to try to capture them or something, I could try counting the number of voles per yard, or probably per acre. Now, we don't have a whole acre of land. Okay, let's pretend you're a farmer. And you're wondering, what's the probability of counting, I don't know, 10 voles in 5 acres of your land? Based on the assumption that you've estimated that there are typically 3 voles per acre on average. So the lambda here would be the fact that you've had a scientist come and count voles for you. Not that they counted every vole, but they've done some sampling, and they've estimated that on average there's 3 voles per acre. Right? Voles they're cuter than moles. I think voles look more like mice or something. 3 voles per acre digging up your farmland. But you are interested in a 10-acre plot of land. 10 acres is not much for a farm, right? Farms are usually hundreds or thousands of acres. But you're thinking about a 10-acre plot of land, and you're wondering what's the probability that there are going to be, maybe 20 or fewer voles on the land there. This would imply that you should expect K equals lambda times S 30 voles on average for 10 acres. I could say 30 voles per 10 acres, but I'll just write in parentheses here for 10 acres. This is actually kind of giving the game away ahead of time as far as the mean goes, right? The mean of a Poisson random variable is K, the parameter K that our textbook calls K. And because of that, actually K is not the most commonly used parameter name for a Poisson random variable. People often just go ahead and jump to the chase and call it mu right away for a mean. You're wondering, if X is counting the number of voles in 10 acres, what's the probability that X is less than or equal to 20? So you would have a 10-acre plot with fewer than the expected number of voles. So the presence of a vole here would be your success. Number of voles per 10 acres. It would be the value of the CDF at 20, capital F of 20. Do we have a formula for the CDF? Well, we do have a formula in terms of adding up values of the PDF. You could theoretically have 0 voles. So X does start at 0, not at 1. Up through 20 here. That would be the summation you would have to do to find this probability. What's the PMF? It's either the negative K, either the negative mu if you prefer. In this case, either the negative 30 power. Whoa, that's a really tiny number. Times K to the X power, 30 to the X power, which could be a really large number once X gets fairly large, divided by X factorial. X factorial gets very large as X gets very large as well. So it's like you got a really small number times a possibly very large number divided by a possibly very large number. Is the fraction itself large or small? Well, it's got to be a probability. It's got to be between 0 and 1. For most values of X, it's not going to be that big. Do you literally have to do the sum? No, use your technology. In this case, use a Poisson CDF would be the quickest thing to do. My calculator is using the letter lambda, not k, not mu. As far as the calculator is concerned, lambda is k. Lambda is mu. Yes, and some people just call it lambda instead. Oh. So our book uses k, but we've seen it is the mean, so we could call it mu. But some people just say, why bother with the lambda k equals lambda times s? Why not just use a lambda to begin with? Of course, that begs a question. Why not just use a k to begin with? It's because different people have different perspectives on things. That's why it's historical. This is the way our book does it, and it's fine. But just realize if you're going to use the calculator, and if your calculator sets it up like mine, lambda is really the same as k. The x value is 20. Paste it, enter it. Should this be large or small? I'm guessing fairly small, even though it's a CDF value, even though it's a sum. Yeah, still fairly small. All the numbers in this sum are fairly small, resulting in a fairly small number in the end. If, for example, we were after f of 20 itself, little f of 20, the probability that x equals 20 exactly, that would be even smaller, of course. But of the terms in the sum, it's probably the biggest one, since the mean is 30. We could do that without using the built-in function. We could do this, although it does make me wonder if these numbers are too big or small for the calculator to handle. What is e to the negative 30 power? Okay, it's using scientific notation. 30 to the 20th power results in a big number, but divide by 20 factorial. Go to my math menu to get the factorial. That's about 0.0134. Say, let's see if the PDF would give the same thing. So now this is the PDF, which we call a PMF. See if it gives the same thing when x is 20. Yep. Got the same thing. So yes, you should be able to do this calculation if necessary, if I ask you to, using the PMF. The summation, you don't literally have to do the summation. I mean, you should realize this is still true. This is going to give you a CDF value, a capital F value. You should realize that theoretically that's what you're doing, but then use the technology to help you do the calculation. I forgot if there's a Poisson table in the back. I think there probably is, but I've looked at it. So yeah, there is. I've rarely ever looked at it, so I was not remembering. Okay, probably best just to use the technology. But yes, you should be able to do this too, if I ask you to show your work there. And maybe even just for extra clarity, even write out what those individual numbers are. Now, probably I would not give you numbers that are so small and large that you'd have to use scientific notation to write them out. But just to confirm that you're computing the right thing, maybe I'd do that maybe I'd be more likely to do that in a business stats class than with you guys, but I'm not ruling it out, I guess. By the way, we do teach the Poisson distribution with the business stats students because it is a really useful distribution. Okay, very useful, for example, like I mentioned with insurance. What's the variance of a Poisson distribution? According to this theorem, the expected value is k and the variance is k. Huh, how can that be? Expected value and the variance are the same? Yeah, for this very special distribution, not in general. What a special distribution. The mean and the variance happen to equal the exact same number. How nice, how easy to remember. The mean and standard deviation are different unless k is 1, right? The standard deviation will be the square root of k. Isn't that weird? Weird, but true. Is it a fortunate truth? I guess so. It's nice. You might say easy to remember if you need to remember it. Like on an actuarial exam, sometimes they require you to remember things like that. So that's nice. You could on the test, if I asked you to, you should be able to use the moment generating function to verify that. Last time, at the end of class last Thursday, we computed the mean as a summation. I actually didn't mean to do that. I meant to compute the moment generating function. You remember I made a mistake. You should be able to compute the moment generating function using the series for e to the x, the Maclaurin or Taylor series for e to the x. That is e to the k right there in the parentheses. You should know that. That's relevant also for the moment generating function theorem about the fact that the derivative of the moment generating function, or the derivatives, first, second, third derivatives, etc., evaluated at 0, give you the first, second, third moments, etc. That series is useful for that derivation. It's also useful for this derivation here to show this equals 1. It's useful for proving that this is the moment generating function. You should practice that ahead of time. It's something you should be able to do on the exam. And then you should also be able to use the moment generating function to verify the mean and the variance. Don't forget, though, with the variance, the answer is not the second derivative evaluated at 0. That gives you the second moment, expected value of x squared. But you've got to use the computational formula for the variance. Second moment minus the square of the first moment, right? E of x squared minus E of x quantity squared. Yeah, people always forget. That's what you got to do for the variance. Like I said before, I even forget it sometimes. Just, you're so excited when you get that second moment, you think it's the variance. No, it's not. It's the second moment. You're almost done. Use it to find the variance. Don't make that mistake. I think I probably have to put a problem like that to find the variance in some way on the exam and confirm that nobody makes that mistake. What's the probability that at least one person will make that mistake? Certainly it's bigger than 0, but I hope it's small, since I keep warning you about it. So yes, you can count the number of successes in more than time intervals. You can count it in areas. In this case, Voles in a certain number of acres. You could count it as with volumes. I don't know, molecules of some pollutant in a square meter of air. Well, that might be a huge number, even if it's a very small concentration. Maybe we shouldn't use it in that situation. But if it was just, I don't know, 10 molecules per square cubic meter, then maybe you could use it. So the Poisson distribution has quite a wide variety of applications. There are some technical hypotheses about something called the Poisson process that need to be satisfied for the Poisson distribution to truly be an accurate model. But to tell you the truth, sometimes people just use the Poisson distribution even if they're unsure if it's a Poisson process. And I haven't said what a Poisson process is. It's kind of a more advanced concept. Maybe we'll have time for it, but not here before exam 1. Maybe later. Maybe a week or two from now. We might have time a week or two from now.